Every system or every component of a big system are modeled mathematically as transfer functions. So the transfer function relates the input and output of a system or a subsystem. And in this episode, I'll explain modeling of the transfer functions. What are the different types of transfer functions? How we can model it using Python control library package. Yes, I'm Leela here, bringing you the second episode in the series Python for Control System. So let us start. How to model the transfer function in Python. So it can be modeled or constructed by various methods depending on how the equation is available. So first method is by direct polynomial definition. So this will take the control from the control system library. The transfer function is taken ct.tf by passing the numerator and denominator coefficients of the polynomial. If the transfer function is known as the ratio of polynomials in the numerator and denominator, their coefficients are organized in the form of an array and they are passed into this function from the control library ct.tf. Here the numerator coefficients are defined by NUM here and DEN represents the denominator coefficients. In the next form, suppose if the transfer function is known in the factored form, that is numerator factors and denominator factors, and we call the numerator factors as zeros and denominator factors as poles, then it is transfer function in Python is represented by the command zpk ct.zpk, that is from the control system library. Zero, pole and gain, that is ct.zpk, will take the input zeros, poles and the gain. So this is constructed, transfer function is constructed if the given transfer function is known in the zero, pole, gain form. We make use of ct.zpk. Here zeros are s values making the transfer function 0, that is the numerator factors value, and poles are those values of h which makes the transfer function infinite, and gain is the constant term that is appearing at the numerator of the transfer function. Next, in the third method, it is the algebraic operator method. In this method, we define s as an operator by using the function ct.transfer function or ct.tf and s as an operator. So define s is equal to ct.tf s within quote, indicating that it is an operator, and we pass the expression as we write on a sheet of paper. So construct the transfer function using this s as an operator. The expression for the transfer function will be formed. The fourth method, which is the state space conversion method. If the state model matrices are known, that is the state matrix, input vector or matrix, output matrix and D matrix are known, then we create the model using the ct.ss, that means state space, ct.state space, and we give this ABCD as the input to this. And we can always convert this state space to transfer function by making use of ct.ss to transfer function, that is state space to transfer function. Okay, so pass this ABCD here and you will get the transfer function. One of the possible ways in which a transfer function can be defined by making use of this ABCD. Then block diagram interconnection. So once we define the transfer function for each block of a system, overall system block diagram, each block, then to get the overall system transfer function, we need to connect these blocks in certain fashion depending on the process which is represented by the individual blocks. So it involves the interconnection of these blocks. So sometimes in some occasions we need to connect them in the cascade, and then we need to connect them in parallel, and there may be a feedback connection also. So how the cascade connection is obtained in Python control library is ct.series then pass the two transfer functions of the subsystems which are to be connected in series. So this ct.series will connect G1 and G2 in series. So we'll get the product G1 into G2. So when we connect two transfer functions blocks in cascade or in series, the resulting transfer function is G1 into G2. So when blocks are to be connected in parallel, we make use of the control function ct.parallel and pass the two blocks which are to be connected in parallel. So this gives the resulting transfer function as G1 plus G2. So the feedback, so we sometimes also have to be connected in, the blocks have to be connected in feedback fashion. So that is achieved by ct.feedback, the forward path transfer function and the feedback path transfer functions are passed on to this in this order. First the forward path and next the feedback path transfer function. So the feedback may be negative feedback or a positive feedback. By default, it is always taken as a negative feedback because in control system analysis and design, we are interested in negative feedback systems. We study the stability and all those analysis and design for negative feedback system, unless positive feedback is only for certain particular applications. So by default, if you don't define anything here, it will take it as a negative feedback. Suppose if you give one more element here, h comma 1, then it will consider it as a positive feedback system. So this is how, and then another important factor that has to be considered is the dead time. So this dead time, what is this dead time? Let me first explain what is this dead time, how it is modeled in the transfer function. So nature of dead time and its physical context. Dead time, it is defined as the time elapsed between the moment deviation or an error occurs and when the corrective action first begins to impact the output. And this is distinct from the transient response, whereas during the dead time interval, the output remains unchanged, whereas in the transient response, the output changes, but it is a transient period before it reaches the steady state. Whereas here, the output does not change at all before the dead time is elapsed. Some example in the control system which involves dead time are, so whenever a signal has to propagate through a medium over long distance, we encounter this dead time. In process control systems where air pressure carries the information through a pipe, let us say, and the signal travels at the speed of sound approximately 330 meters per second, and if the pipe is of 330 meters long, then there is 1 second dead time before the pressure change is felt at the other end. So you can imagine this 1 second dead time, how much impact it will have in this pressure control system whenever there is some mitigating approach is implemented to bring about some change in the output pressure. So this delay will cause a lot of errors and deviation from the set response. So that has to be mathematically properly accounted for in while constructing the transfer function itself. So another example is a pipeline flow. In a heating system, hot water has to travel through a pipe to a distant radiator. Let us suppose that the hot water has to be carried to a distant radiator. Then the temperature at the radiator does not begin to rise until the water has traveled this length of pipe. So this time elapsed between the instant at which the pipe water flow is turned on and to the instant at which the water reaches the radiator, that is the dead time that is encountered in this pipeline flow example. Similarly, in a chemical reactions, so adjusting a valve to change the reactant flow in a long pipe will result in a delay before the chemical composition in a distant reaction vessel changes. So you can imagine how this delay will cause the further processing or further changes that take place in the whole of the control system. So they have to be properly modeled mathematically. So how these dead times are modeled? So they have to be modeled in the S domain, appropriately considered along with the other system blocks. So in the Laplace domain, the dead time is represented by an exponential term e to the power of minus tau s, where tau is the time delay. So the exact transfer function of the system with delay is expressed as g dash of s is equal to e to the power of tau s into g of s, where g of s is the system transfer function without delay, and a delay is accounted for by by connecting e to the power of tau s in cascade with the g of s. But Python control library, it is designed to manipulate the transfer function which is in the rational form, that is the ratio of polynomials in S. So it cannot directly simulate this e to the power of tau s term without converting it into a rational form. So integrate this dead time into Python based models. Pade approximation is used, and this replaces this exponential term with a rational transfer function, approximating it to a specific order n. So depending on to what accuracy we need, we decide the order of this approximation for Pade approximation for this dead time, and construct the transfer function of the system with dead time. Coming back to the dead time modeling, how this is modeled in Python. So we make use of Pade approximation from the control system library ct.pade. Give the delay and the order. So delay is tau, order is capital N. Then get this, designate this as g dash of s and connect that in series with the base transfer function g of s. This is how we construct the transfer function using Python if there is a dead time present in a system. Next, let us see how we can do it. We'll take you to Jupyter Notebook and explain with the examples how to construct the control system, how to make use of the control system to construct the transfer function in different forms. So creating a transfer function of a continuous time LTI system using Python. So prerequisites and setup. So before we start creating the transfer function, we need to import the important libraries required for this. So first one is NumPy, and we import it as NP, and import control as ct. So let me execute this and see if there is any error. So it has passed. So next is, first method is by using polynomial coefficients. Here is an example. G of s is equal to 2s plus 1 by s square plus 4s plus 6. This is the transfer function which has the numerator polynomial 2s plus 1 and denominator polynomial s square plus 4s plus 6. So after importing the necessary libraries in the first step, we define the numerator and denominator coefficients as arrays. So the numerator polynomial is 2s plus 1, so it will have the array elements as 2 and 1. Starting from the highest power of s to the least power, we need to arrange the coefficients in the order of decreasing powers of s, and we need to reach up to s power 0, even if the term is not present. Whichever term is not present, we need to take the coefficient as 0. So here the numerator is 2s plus 1, so the array takes the form 2, 1. So we define the numerator as NUM, they designate it as NUM, and NP dot array, we take the NumPy array and construct the numerator array with the coefficients of the numerator polynomial 2 and 1. Similarly, the denominator is designated as DEN and the NumPy array is constructed with the coefficients of the denominator polynomial starting from the highest power. Highest power is a square, its coefficient is 1, so the first element is 1. Next is 4 and the least is s power 0 whose coefficient is 6. So 1, 4, 6 forms the denominator array. So after defining this numerator and denominator array, we pass it on to ct.tf function, that is from the control library, take the transfer function and pass the numerator and denominator arrays and print that transfer function designated as g here. So if I execute this, I get the transfer function g as 2s plus 1 by s square plus 4s plus 6 as required. So in the next method, this is by defining the s operator of the Laplace as an algebraic definition. So again, the first step is to import the necessary libraries, and next we shall define this s in the ct.transfer function dot s. So we define s as an algebraic operator. So whatever the equation that we give, it takes it as an algebraic operator and construct the transfer function. So s is equal to ct dot, either in the full form you write it like this, transfer function with t and f capital letters, or in the short form you can even replace this by ct.tf dot s. So this additional dot s will take the s as an algebraic variable. So g is equal to, now whatever the equations, the numerator polynomial and denominator polynomial, we just type it as it is, replacing the multiplication by the symbol one single star and the power by double star. So s 2s in the numerator is written as 2 into s, that multiplication sign is represented by a single star, and in the denominator s square, s raised to the power 2 is represented by, that rising is done by double star here. Okay, so 4 into s, again a single star to represent that it is a multiplication. So once we pass the numerator and denominator polynomials in this form, we ask it to print it. Let us see what it does by running this script. So we have gs is equal to 2s plus 1 by s square plus 4s plus 6 as we have given. That is what is required. So this is how we designate this s as an algebraic operator and pass the given transfer function as it is by replacing the multiplication and power by these symbols, and that also constructs the transfer function. So in the third method, if the transfer function is expressed in pole zero gain form, so we shall import the library, control system library, because we are not making use of any other libraries here. This itself is sufficient. So we define we designate the transfer function by name, say H here, and ct.zpk. So zpk represent that in the order 0, pole and k that has to be passed on to this. And the zeros, poles and poles are to be in the form of lists. So ct.zpk within the curve bracket, we pass the list of zeros, list of poles and the gain. Here the example taken is h of s is equal to 10 into s plus 1 divided by s plus 2 into s plus 5 into s plus 7. So here the zeros are at s is equal to minus 1, there is 1 0, and 3 poles at s is equal to minus 2, minus 5 and minus 7. So the 0 is passed as a list containing the 0 at s is equal to minus 1, that is the list with minus 1. And poles are at minus 2, minus 5, minus 7. So a list is formed with minus 2, minus 5, minus 7. And that is passed as the second element in this zpk. And the gain is whatever the overall multiplying factor here is taken as the gain. And here it is 10. So that is passed as the third element for this zpk. So we'll ask it to print this transfer function. So let me run this, shift and enter. So our h of s is 10s plus 10 by s cube plus 14s square plus 59s plus 70. So if you multiply these three terms, you will get this polynomial. You can verify that. And the numerator polynomial is 10s plus 10. So this gives the transfer function in the polynomial form. So in the fourth method, creating the state space representation. So in this state space, the representation of the transfer system is by means of state equations. X dot is equal to ax plus bu, y is equal to cx plus du, where A is the state matrix, B is the input matrix or vector, C is the output matrix or vector, and D is the direct transmission matrix. So this ct.ss will take these four matrices as the input, and it designates it as a state space representation of the transfer function. So how we can give these matrices as inputs to the ct.ss? So again importing the libraries of NumPy and control. So how we can form these matrices? A is equal to A is a state matrix of n by n, and here let us suppose that it is a 2 by 2 matrix with first row as 0 and 1, second row as minus 1 and minus 3. So each row is represented by means of an array, and a comma separates the number of each row. So here the first row is 0, 1. So this array represents the first row of the matrix A, and comma will indicate that we are moving to the second row, and the second row is again an array with minus 1 and minus 3. So this is passing this within this curved bracket, and before that overall square bracket indicating that within these square brackets of the outer square brackets we have the arrays representing each rows. So this np dot array within the curve bracket, we pass this row arrays within this outer square bracket. So whatever may be the order of the matrix, depending on the number of elements in the row, this will have a number of elements each row, and depending on the number of rows, each row is separated by means of a comma. So this is the matrix A. And similarly, the B vector or a matrix. So if it is a vector, it will have only one element in each row. It's a column vector. And a row vector, like in the matrix C, the output vector C, this is a row vector. You see here, it has got two elements in only one row. So this enclosed within the outer bracket represents that there is only one row. If there were to be more rows, it would have been separated by means of a comma. So this is a row vector, whereas this is a column vector. So a column vector with one element each in each row. So you see that first element is 0.0, then comma, the second row is 1.0. So this is a 2 by 1 vector, this is 1 by 2 vector. And D vector or D matrix is 0, so we pass 0 elements to this NP dot array. So let us see how it prints the matrices. Shift and enter. So I have not given the command to print it, so it has not printed, it has taken the elements. So in the next step, state space model. So SS underscore model, this is the designation given to this ct.ss, passing this A, B, C, D and asking it to print each of these. Well, let us see what it gives. So here is the matrix A, first row, second row within the outer matrix designation, and B, first row element, second row element within this overall representing a column vector, and C is a row vector, and D is this. So we can convert the state space to transfer function or transfer function to state space. So how to convert the state space to transfer function? So let us designate the transfer function as h underscore state space to transfer function. Here for recognition I am given this, you can give any designation for this. So ct.ss to tf, then we'll pass that ss underscore model we constructed in the earlier step, and we'll ask it to print the transfer function from state space model, giving this, passing this designation that we have given for state transfer function model that is to be constructed from the state space. So here from state space it has obtained the transfer function as this 1 divided by s square plus 3s plus 1. So this is a second order system since our A matrix is a 2 by 2 matrix. So we can even do transfer function to state space by just reversing ts to ss, and that will construct one of the possible transfer function from the given state space representation. So that can be tried as a task by you. So next, let us see how we can combine these transfer functions in series, parallel, feedback, etc. So this is the necessity of having this combination of the various systems. So we shall define the systems. So we have taken two systems, G1 and G2. G1 is 1 by s plus 1 and G2 is 5 by 2s plus 1. For demonstrating the various combination of the transfer functions, these are the two examples for the subsystems that are chosen. So first we shall take the two transfer functions G1 and G2 and construct it using the NumPy array, defining the numerator and denominator. For the first transfer function G1, I am designating the numerator and denominators by NUM1 and DEN1 by passing the numerator array and denominator array. So here G1s is 1 by s plus 1, so the numerator will have only one element, and denominator is a first order polynomial, so it will have the components 1, 1. So pass this numerator 1 and denominator 1 to construct the transfer function using ct.tf and designate it as G1. Similarly, define G2 of G2 which is given as 5 divided by 2s plus 1. So the numerator constitutes a single element 5, and denominator is 2, 1. So we designate the numerator and denominator arrays by numerator 2, denominator 2, and pass these two to construct the transfer function by ct.tf and designate it as G2. And we shall ask it to print G1s and G2s, which is constructed as G1 and G2. So let me run this. Now you see it has constructed G1s as 1 by s plus 1 and G2s as 5 by 2s plus 1. So let us see how we can connect this G1 and G2 in series. So H underscore series is the resulting transfer function when G1 and G2 are connected in series. To connect them in series, we make use of the control system library package function ct.series. So ct.series pass the transfer functions which are to be connected in series and print that transfer function. So let me execute this. So when we connect this G1 and G2 in series, it will be G1 into G2, that is 1 by s plus 1 multiplied by 5 by 2s plus 1. So when you carry out the multiplication of the denominator, you get 2s square plus 3s plus 1 and numerator is 5 into 1, that is 5. So this is the resultant transfer functions which resultant of the transfer functions which are connected in series. Let us connect the same two transfer functions in parallel. So when we connect them in parallel, it may be addition or subtraction of the two transfer functions. It may take the general form of G1 plus or minus of G2. So let us see how we can do it. So ct.parallel is a Python control system library function that is taken to connect G1 and G2 in parallel. So if you don't designate, give any other information, it will take it as by default the addition of the two subsystems. So let me run this. So this is G1 plus G2. And you can check whether the numerator and denominator polynomials are correct. That is 1 by s plus 1 plus 5 by 2s plus 1 will result in this numerator and denominator polynomial. So how we can do it if it is a subtraction? If it is a subtraction, you just give this, multiply this G2 by minus 1. Then it will add this G1 with minus G2 and give the parallel combination. So this is what you get when you execute this. So to connect them in parallel with a negative sign, that will subtract, and if you don't define anything, it will take it as a addition. So next we have feedback combination, a closed loop system with a feedback from the output to the input. So by default, it will take it as a negative feedback, and a transfer function of a negative feedback system with forward path transfer function GFS and feedback path transfer function HFS is GFS by 1 plus GFS into H of S. So let us see what happens when we connect G1 and H in parallel. So let us define G1 or GFS as 1 by S plus 1. So the numerator array is 1, denominator is 1 comma 1, and we shall take the feedback path as a unity feedback path. So with the unity feedback path, the transfer function ct.hf is numerator 1 and denominator 1, and we define the second transfer function g2 by 5 by 2s plus 1 in this. So that is what is done here. And we shall give the h as a new transfer function with numerator 2 and denominator 2. So print g and h, and taking this h, sorry, it is not unity feedback, taking this h as the feedback transfer function and g as g that is constructed here with numerator and denominator, that is 1 by s plus 1, and h constructed with the numerator 2 and denominator 2, that is our G2 earlier, which was our G2 is now our H. We shall connect these two in parallel, feedback, negative feedback first. So a feedback transfer function designating it as h underscore feedback ct.feedback g comma h. So let us see what we get. So this is our forward path transfer function, this is our feedback path transfer function, and this is the combined negative feedback transfer function with the negative feedback. Suppose if it is a positive feedback, then it will be minus here. And how to account for it? So in the feedback that is ct.feedback, just add 1 to this. Pass 1 to 1 as third input to the ct.feedback. That will construct the positive feedback system. So with positive feedback, it can be verified that this is the system. So using Pade approximation, so modeling the time delay. So let us suppose that tau is the time delay and transfer function is e to the power of tau s for the time delay function. So let us have a transfer function h of s, h1 of s given by kh divided by theta underscore t into s plus 1. Okay, so which is, let us define a transfer function with 3.5 divided by 22 s plus 1 is our original transfer function, and we construct it by passing the numerator and denominator coefficients. So for a general transfer function, it is the numerator is kh that is passed here, and denominator theta underscore t and 1, that is theta t plus 1 is the denominator that we are taking as the denominator elements. So passing that to ct.tf, we construct h1. So I must get h1 as 3.5 by 22.1. Since I have defined these parameters in the beginning of the script itself, kh is 3.5, theta t is 22, and theta d also is given here, that is the time delay which is required in the next step. Okay, nothing, it's not asked to print anything, so it has not printed. So let us define the order of the Pade approximation as n underscore Pade as 5, and the numerator and denominator of the transfer function of the Pade approximation ct.Pade is equal to Pade, and we pass this delay and the order of the Pade. So create the transfer function representing the delay as h Pade ct.tf, the numerator and denominator. Okay. So this ct.Pade with the delay and the order will generate an array with numerator and denominator coefficients of the transfer function. So those coefficients are passed on to ct.tf to construct the Pade transfer function with Pade approximation. So next print this h Pade and then combine this transfer function with the normal transfer function of the system without the time delay in cascade h1 and h Pade. Then print that also. So let me run this. So we shall see here with order 5, the Pade approximation is given by this e to the power of tau ds, where tau d delay was given as in the previous stage itself. We have taken the delay as 2 and order as 5. With delay 2 and order 5, the Pade e to the power of tau s is approximated by this polynomial in the numerator and denominator, and then that is clubbed with the h1. So where H1 we created earlier, and when they are connected in cascade, we get the transfer function given by this. So this is how we make use of Python control system library functions to define or construct the transfer functions when the transfer function is available in various forms. So we make use of ct.tf to construct the transfer function, and before that how we have to define the elements of the transfer function depending on whether the transfer function is available in the form of polynomials in the numerator and denominator, polynomials of s in numerator and denominator, or pole 0, 0 pole and gain, or if it is a steady state model of the transfer function, and then some simple connections of the subsystems in series or parallel and feedback, and further how we can approximate the time delay by Pade approximation and continue with the analysis of the control system. So with this we come to the end of episode 2. Stay tuned for the next episode.